Hello and welcome everyone to today's edition of Loxone Explained. I'm thrilled to have Sebastian and myself here representing the Loxone Campus heroes. As a team, we have initiated our primary goal, which has been to contribute to the development of the Loxone Campus. This started from the initial planning phase and extended all the way through the installation. We've dedicated ourselves to overseeing every aspect of the project, even through to the intricate details like the LED spots, the loudspeakers, etc. Today we will talk about the important topic of energy. Whether you believe in the existence of an energy crisis or not is inconsequential. The undeniable reality is that energy comes with a substantial price tag. So now let's delve into the specific tools we've employed to measure energy consumption on the Loxone campus. So for heating distribution, what are the names of the products we've utilized here for accurate measurement?
The Belimo energy valves account for all the heat energy that goes into the Loxone campus. So we can track the energy flows into each of the different areas, and therefore we can make targeted improvements in individual areas if necessary.
Yes, Sebastian, we have underfloor heating, exactly. Then we have the induction units on the ceiling too. Let's explore the heating and cooling medium in more detail. Our campus office, spanning a considerable 3,000 square meters, relies on the regulation of air temperature, which is both supplied and extracted. Additionally, when the CO2 levels reach a certain threshold, we initiate ventilation by introducing fresh air from the outside. Ventilation holds a significant potential for energy saving. To begin addressing this, we need to perform some calculations. Specifically, we need to determine the annual cost of 1 watt of heat power.
1 watt a year costs about €1.
Our approach to energy saving revolves around a rule of thumb, identifying the most accessible opportunities that yield significant energy savings and provide a fast and effortless return on investment. For instance, while peak consumption may occur during 2-hour daily operation of the sauna, its impact on annual consumption is relatively minor. The focus lies in comprehensively assessing the overall energy usage composition by pinpointing areas of utmost importance to the building owner. In this context, you mentioned that 1 watt of heat output costs approximately €1 per year. Now, let's shift our attention to electricity. Where do we typically begin when addressing electricity consumption?
Electricity? We are currently calculating with €2.50.
So 1 watt of electricity costs €2.50 a year. Because that 1 watt is used 24 hours a day with 60 minutes per hour and 365 days per year, the amount really adds up. But that is not important in our consideration. Whether we are exactly on the same decimal point doesn't really matter. We are actually only concerned with a certain dimension, which in practice means what is the heating capacity at 0 degrees light today in the campus.
Heating in the office. We approximate the use at 80 to 100 kilowatts. So 80 kilowatts, that's 80,000 watts and €80,000. If we were to calculate for the whole year, but we only heat in the winter.
Exactly, and of course the question is, how much can be saved and where do the savings come from? Why is it possible to save anything at all? Because it should actually be warm everywhere anyway. And so we will look at this a bit more closely now by going to our main power consumers, to our friend the... Has the NFC been completed? Today, a new development has come into effect. However, an oversight regarding the NFC has caused significant disruption. Access to the technical infrastructure now requires a key, which has led to a bit of confusion. This includes one of our ventilation centres, which is crucial for maintaining optimal conditions in the 3,000 square metre office. However, it's important to note that this particular ventilation centre should not be taken too seriously, as we always have our emergency measures in place to ensure our safety, as evident from the various devices present here. The hall's heating is currently managed by a mini server, since the distributor is not yet fully operational. It's worth mentioning that not everything is fully functional at the moment. The remarkable aspect is our newfound ability to regulate energy distribution through the ventilation system, which happens to be our largest energy consumer. Given the circumstances, what would be your estimation of the current performance values in terms of energy consumption?
So now, in the office, in the afternoon, we will still be heating somewhere between 10 and 15 kilowatts.
Mario is another campus hero in the wider team. He is heavily involved in the ventilation. We started with somewhere around 60 kilowatts.
60 to 80 kilowatts on just the ventilation itself.
Now let's practice our maths again. 60 kilowatts for half a year is how many euros? 30,000?
30,000 euros.
The ventilation system incurs a considerable annual cost in heating expenses. One drawback of ventilation is the intake of cold outside air, especially during winter when temperatures can reach or dip below freezing. We must then expend energy to raise this air up to room temperature. To mitigate this, we have implemented heat recovery mechanisms and other techniques to initially warm the air. However, additional energy input is still required, currently amounted to 12 kilowatts. This becomes a crucial factor in solving the puzzle determining the optimal amount of fresh air that needs to be drawn in and heated. This leads us to the first topic at hand: how much ventilation is necessary for each specific area. Moreover, we need to address the issues of energy distribution within the system. Could you please provide a brief explanation regarding the valves that we employ in this context?
Of course. So on this side, there is always the power distribution. We have a mixer circuit here, and in each mixer circuit, we have the return as an energy valve. The energy valve acts as a mixer for us, which allows us to set the ideal flow temperatures in the individual circuits, plus also have the integrated power measurements at the same time.
Let's envision the energy valve as a mixer with additional functionalities. It not only blends the flow of different temperature streams, but also incorporates temperature measurement using a flow meter. This measurement provides us with valuable data such as power and energy usage. Our mini server diligently records this information, allowing us to track consumption accurately. Now we find ourselves in front of a temporary Loxone control system installation, which might receive some critical remarks in the comments.
But the new control cabinet is already there and will be put into operation next week.
This phase has been crucial for us as we initially installed the ventilation system with standard programming, similar to that of any regular building. From there, we gradually fine-tuned and optimized its performance to maximize energy efficiency. Our goal is to extract the utmost benefit from the energy resources available. At present, the ventilation system operates at approximately 11 kilowatts, although the value can vary depending on the number of occupants present in the office. If the occupancy increases significantly, we might need to draw additional energy from the external power grid. However, around 9 o'clock a remarkable shift occurs, marking the phase where we achieve energy neutrality. During this time, the need for active heating diminishes significantly. Sebastian, could you please provide a brief explanation of how the ventilation center operates?
Our supply air is found here. So that's where the fresh air comes in from the outside. Then it goes across the heat exchanger. We get, of course, as much heat energy as we can from the exhaust air that's leaving. Then we have two supply air fans here. There is a heating coil you can see here. These are the silver-clad pipes, which are always heating. Then there's the cooling coil, which are the black insulated pipes. And then the air gets taken off into the office, and up here is coming back from the office with the exhaust air, which is pumped out via the extract fans. It then goes through the cross heat exchanger again and is either released outside or is used again in recirculation mode. Recirculation mode is the mode that we actually run 95% of the day because more often than not, you don't need the fresh air as the CO2 levels are not high enough to need outside air.
So far, it is only a construction site, so it's fair to say that the maximum air is at a nominal value.
Output is around 20,000 cubic meters per hour.
That's what we are all really breathing in the office. How much is it currently?
At the moment, we will be somewhere between 6,000 and 7,000 cubic meters.
The ventilation system operates in a self-sufficient manner, relying on the information provided by the mini server located in the office. The primary objective for managing the 6,000 cubic meters of air is to achieve high air quality whilst minimizing the amount of ventilation required. It is essential to maintain the CO2 levels below 1,000 parts per million. The key factor influencing energy consumption is the fan speed. A lower fan speed results in reduced ventilation and lower electricity usage. However, our priority is to ensure that the air requiring heating and tempering is properly circulated. The 4 fans in operation are ETM fans connected to a Modbus extension, allowing us to control the entire system digitally. The digital control eliminates the need for analog control elements in the ventilation process. The digital interfaces simplifies operations, and the fans can provide error messages if any issues arise, ensuring prompt problem identification. The distribution board demonstrates a substantial power line, indicating the manageable size of the distributor. We are fortunate to have skilled colleagues dedicated to the distribution area. Within the distribution setup, we have various components linked to the analog extensions. Could you please provide details about the specific devices connected to these analog extensions?
Analog. We currently have CO2 probes and pressure sensors in the air ducts.
To ensure efficient functioning of the control system, we have found that some aspects still require analog measurement. For temperature measurements, we utilize one-wire technology throughout the entire control system, all extending from the central ventilation unit. This blending of digital and analog elements is intriguing as it demonstrates the effectiveness of the Loxone software, which significantly reduces the need for additional hardware products. We have achieved comprehensive energy monitoring with a remarkably streamlined system. One of the advantages is that a person familiar with the mini server and its configuration can easily control the ventilation center, even without prior expertise in the ventilation systems. This not only keeps costs down, but also allows for seamless management by a skilled individual. In the event of malfunction, which is a natural occurrence in the life cycle of any ventilation system, the configuration expert can simply log in and identify this exact fault location. Once identified, the expert can rectify the issues as easily as replacing, for example, an LED spot in the office. This future-proofing aspect of the system is crucial, offering flexibility and ease of maintenance. At Loxone, our focus extends beyond turnover. Instead of relying heavily on proprietary Loxone hardware within the ventilation center, we empower our partners and customers by utilizing our powerful free software. This approach ensures a cost-effective solution and provides greater flexibility for all involved. Now let's explore the programming and wider hardware setup of the ventilation system, as well as delve into desired energy flow configurations. Sebastian, in terms of architecture, we've segmented the 3,000 square meter office into segments. Can you tell me how many segments we've made here?
We currently have 14 segments.
Within each segment, we have a dedicated mini server forming part of a comprehensive client gateway network. Each mini server is responsible for controlling the ventilation system within its respective segment using specialized ventilation modules. This setup offers remarkable flexibility, allowing us to precisely manage the opening and closing of ventilation pipes based on the mini server's commands. Through a process of network intercommunication, we transmit the ventilation requirements to the central ventilation center. Here, the most crucial decision is made whether to initiate ventilation or not. This decision holds great significance as ventilation comes with associated costs. The fan motors consume electrical current, and in addition, there's the energy expenditure for heating during winter and cooling in summer. Our objective is to minimize unnecessary ventilation. We strive to ventilate when it is truly necessary rather than simply when it is possible. This principle of prioritizing necessity over mere possibility is consistently applied throughout our network intercommunication protocol.
We are currently sending the request as well as the largest opening angle from the volume flow controllers. The background behind this is so that we can mostly control the ventilation from the shutdown fan speed. This makes it more energy efficient.
Om einfach energieeffizient zu arbeiten.
We have conducted various experiments to optimize energy consumption, including implementing measures such as bar point control and adjusting air concentration based on presence. These situational organizations allow for tailoring the system to specific needs. Additionally, this send data to the Gateway mini server, which serves as our current energy monitoring mini server. Let's now focus on our energy monitoring. With our current setup, we are drawing 162 kilowatts of power into the office while utilizing only 3.4 kilowatts for heating the 3,000 square meter area. We'll explore the specifics of this shortly. Out of the 3.4 kilowatts, a significant portion is allocated to ventilation, with the heating plant preconditioning the air. Interestingly, this consumption is lower compared to our previous setup. The underfloor heating is set to a basic temperature control, allowing us to conserve energy by not utilizing it. Throughout the day, there is a clear trend in energy usage. Although the exact details may not be of immediate importance, one noticeable phase is the morning heating period, during which we allocate slightly more energy. The Belimo energy valves play a crucial role in our energy optimization efforts. They provide essential power and meter values, which enables us to monitor and analyze energy usage effectively. Having access to this data is paramount for our optimization endeavors. We have also established a digital connection from Tree to Belimo via an interface, and programming it was a relatively straightforward task. It can be considered a plug-and-play integration. Looking at heat usage, we observe that 5.6 kilowatts is dedicated to the warehouse area, which will soon be operational. Additionally, there are radiant ceiling panels in general areas consuming 26 kilowatts. While these areas are currently under construction, the heating system is already functional. A significant proportion of energy is allocated to tasks related to baking screed and other construction site activities. Despite the outside temperature being around 5 degrees, we managed to heat the 3,000 square meter office with just a few kilowatts, allowing for slight fluctuations based on the current temperature. This approach is key to our energy saving efforts. Yesterday we had an interesting day as we focused on identifying and locating an energy leak within the system.
Das Wetter ist nicht schön, es ist nicht sonnig und wir heizen 3000 Quadratmeter bei 5 Grad Außentemperatur.
Yes, we've had relatively large consumers. The rest is in the heating, where we were initially unsure as to exactly where the energy was flowing. So we looked into it and found there was a few valves which were not yet connected. And so we're always in the manual position, which was set to 100% on flow. So we closed them by hand, and this solved the mystery, getting rid of the energy leak.
The level of energy management we have achieved is a direct result of our comprehensive monitoring system. It enables us to precisely track the amount of kilowatts we draw from the local heating system and the specific energy consumption within the office. The data is instrumental in identifying and eliminating any unnecessary energy usage, contributing to the overall energy efficiency of the building. Accurate records of energy consumption are essential for effective energy management. Now let's shift our focus to electricity usage. Although we previously discussed heat, it is worth noting that we are currently not using any cooling systems due to the cold weather. On the electricity side, we observe that our partially operational photovoltaic system continues to generate 25 kilowatts even in unfavorable weather conditions. Our total consumption stands at 71 kilowatts, but upon closer examination we find that 44 kilowatts is drawn via our transformer. The most intriguing aspect lies within the campus office, where our total consumption is a mere 3.2 kilowatts.
This is now the whole 24-volt electrical system, which speaks for all the power supply and backups, which we have summarized there, which currently have a total output of 3.2 kilowatts.
We've set up all the audio equipment here. Can you tell me how many speakers we've installed?
Speakers, we have just under 100.
900 tree spots.
Within our premises, we have installed over 900 tree spots, and we can provide further details as needed. In our designated in this space area, which refers to our company space, the energy requirement is impressively low, amounting to only 189 watts, taking A closer look at specific components, the mini server and its extensions consume 3 watts, the speakers operate at 31 watts, and peripheral lighting utilises 49 watts. While we don't need to delve into every detail, it is noteworthy that we achieve a resting consumption of 31 watts. For such a large space, this is remarkable. Once our team starts arriving at around 6:30 am, energy consumption naturally increases as we activate lights, play music and perform other tasks. In this segment, the energy usage reaches about 190 watts, which is quite impressive. Moving on to our base camp, which is our previous building, the consumption stands at 38 watts. Our chef continues to work and we have guests charging their electric cars in the underground parking lot on the 2 active wall boxes. The remaining 30 kilowatts is being utilised at the construction site. Our energy monitoring system is designed to provide precise insights into energy distribution. We monitor every detail, even in the high voltage sector. We have implemented high voltage systems operating at 230 volts and 400 volts, allowing us to form segments and analyse their specific details.
Quasi bis ins letzte Detail aktiv und im Hochspannungsbereich Gebäude.
This visibility into our energy usage is crucial for understanding and reducing our overall consumption, and it has already proven to be immensely helpful. For instance, we have gained valuable insight into the heating performance of our construction containers. Could you please share more information about their performance?
Wie war das mit der Heizung bei den Baucontainern? Was haben die für Leistung?
Now, with the temperature at the weekend,
They were running at 5 kilowatts, which is quite low considering they peaked at 13 kilowatts. Can you remind me what we calculate the annual cost of electricity to be?
Mit welchem Preis jetzt nochmal angesetzt im Jahr?
30 cents per kilowatt hour, which brings us up to the €2.50 at 1 watt load.
Our primary objective is to achieve a significant reduction in energy consumption. To accomplish this, we have initiated a project in our existing building with 2 team members dedicated to identifying areas where we can effectively reduce electricity usage. The 50 kilowatts of energy we discussed cannot simply disappear, as energy laws dictate. Instead, it is converted into heat. While this is acceptable during winter, it becomes undesirable during the summer when we seek to avoid excess warmth. Therefore, we must counteract this heat build-up by expending the same amount of energy in cooling processes. Visibility plays a crucial role in managing these services effectively, and our energy flow monitor provides us with necessary insights. This feature is available free of charge. All you need is the integration of a meter. Could you please explain the function and purpose of the transformer within our energy system?
Dazu den Schlüssel, so kostenloses Feature, man braucht nur die Zählerintegration. Was ist der Trafo?
Der Trafo ist ein
The transformer is a meter with wandering terminals, which we currently read via the Modbus.
What power do we currently have there?
Trafoleistung.
Die Wandler.
We currently have 630 kilovolt transformer power.
Thank you for providing this explanation. I understand that we acquire transformer measurements from the energy supplier or grid operator, which are recorded and compared to the figures stated on our invoices. This meticulous monitoring enables us to effectively track our energy usage and identify any instances of excessive consumption. Our ultimate goal is to address these areas and implement measures to reduce and enhance control over our overall energy consumption. Finally, let's take a look at the construction site here, which will soon be our auditorium. Can you remind me how many spots we've installed here?
About 210.
Wirklich schauen, Energiemonitoring, das ist der Schlüssel zum baren Geld. Es ist einfach so.
We can also see some power supply and backups here. Before concluding, it's important to note if you're running a business, it's essential to monitor energy consumption. It's the key to saving money. If you're not sure how to get started, reach out to a Loxone partner. We've also provided intensive training for all of our partner coaches around the world on this topic of energy monitoring. So even if you're a Loxone partner and you might not have extensive experience in this area, then you can turn to your partner coaches for help. It's crucial to understand and interpret this energy trend, whether it's heating, cooling, or electrical current. Being able to read and recognise this trend is the key to the entire process. We thank you for watching and look forward to providing you with more insights into our groundbreaking campus headquarters project in the near future. Stay tuned for more Loxone Explained videos coming soon. Thanks again for watching.
Loxone Explained mit einem starken Insight präsentieren können. Dankeschön.